When someone tells me, we've already been to the moon, Mars is just a little farther, I always pause. Not to argue, but to ask myself, do you really understand what you just said? We're used to looking at the universe as simple numbers. 384,400 kilometers to the moon, a small hop in space. Apollo 11 covered that distance in 3 days, and Apollo 13 even turned back when life was hanging by a thin thread. It all makes us think distance is no big deal, but try answering this question. What really changes when we stretch that distance not just double, but hundreds of times over? Mars isn't a few 100,000 kilometers away. It's 55 to 401 million kilometers, depending on where the planets are in their orbits around the Sun. A trip takes 6 to 9 months, and while you're drifting in that deep space, there's no turning back, like in 1970, no rescue team, no shortcut, no hand reaching out from Earth. We often talk about Mars as a higher goal, but the harsh truth is far more brutal. The moon is just the first step. Mars is the boundary where the universe truly starts to become alien, where all our simple notions of near and far completely collapse. When you look straight at that difference, you understand this isn't about distance. It's about the unforgiving nature of deep space. You know, Newton wrote his laws of motion in 1687. And strangely enough, those classic lines still determine the fate of every spaceflight dream today. The principle of a rocket is actually very simple. You throw something backward, and by Newton's third law, you get pushed forward. But that simplicity hides a much crueler truth. In 1903, Konstantin Tsiolkovsky wrote the equation that precisely describes how a rocket accelerates, and it became the foundation of all modern space travel. To V equals V times ln mf. It sounds harmless, but look closer. That n, the natural logarithm, is the thing that makes all your intuition betray you. A rocket doesn't just carry fuel, it has to carry fuel to carry the fuel. That's why I say a rocket is a machine that must carry its own future, and the future is very heavy. The best chemical engines we have today give an exhaust velocity of about 3.2 to 4.5 kilometers/ss. And to gain just 1 or 2 kilometers ss more speed, you might have to double or even triple the total mass of the rocket. Falcon 9, one of the engineering marvels of the era you're living in, has 94% of its mass as fuel when it leaves the pad. Saturn V, the giant that took humans to the moon from 1967 to 1973, carried 85% fuel. Those two numbers show what the logarithm is telling us. The universe doesn't care about human logic. It only obeys its own cold numbers, and in those numbers the logarithm is a tyrant, silent but absolute. Now, if you really want to understand why returning from Mars is almost an impossible task, you have to look straight at what engineers call the delta-v budget. The cold measure of how much velocity change you need to complete the entire journey. Every meter per second you want costs fuel, and fuel has mass, and mass is expensive. The whole story starts in the same place, Earth. Whether you're going to the moon or Mars, you have to pay the fixed toll to climb from the ground to low Earth orbit, LEO, about 9.3 to 9.5 kilometers/s. This is the most expensive part of the entire journey. Most of the fuel in any rocket, Falcon 9, SLS, or Saturn V, is burned just to escape our planet's gravity well. No current technology changes that. LEO is the mandatory gate. There's no way around it. From there we can start comparing. During the Apollo era, from 1969 to 1972, NASA made 6 moon landings. The astronauts started from LEO, then performed a translunar injection burn of about 3.2 kilometers/s, sending them on a 3-day journey to the moon. Upon arrival, they slowed by about 0.9 kilometers st enter orbit. Then came landing, just 1.6 kilometers STSTS for powered descent, thanks to the moon having no atmosphere, no wind, no friction, no surprises. It's a world so quiet you can program a landing path with almost pure mathematics. Leaving the moon was even easier, just 2.7 kilometers to reach lunar orbit, then fire back toward Earth. And when you got home, Earth did the rest. Gravity pulled you down, the atmosphere slowed you, and you splashed into the ocean. Total Delta V budget: 15 to 16 kilometers/z. That's a huge number, but it's one Saturn V could handle. Humans accomplished what seemed impossible with 1960s technology simply because the moon favored us. It's close. It's small. It's silent. It has no atmosphere to burn you up, and its gravity is so weak you can leave it with an engine weaker than a modern car engine. But now look at Mars Zand. This is where human intuition betrays itself. To leave LEO and set you on a path to the red planet, you need 3.6 kilometers tel/Rs for trans-Mars injection. It sounds not too different from going to the moon, just farther, right? But the problem isn't in the absolute number, it's in what happens next. When you reach Mars, you have to slow down 1 to 2 kilometers/s to enter orbit. But decelerating at Mars is far harder than at the moon, because there is an atmosphere but only 1% the density of Earth's. It's too thin to help you brake effectively like on Earth, but thick enough to incinerate any hardware without a proper heat shield. The perfect paradox in our atmosphere to cause trouble, but not enough to help you. That's why every NASA robot landing is called 7 minutes of terror. After slowing with a heat shield and parachute, you're still plummeting toward the surface at deadly speed. For robots under 1 ton like Curiosity or Perseverance, NASA could use retropropulsion for the final seconds. But imagine landing 20 to 40 tons, the minimum mass for a crewed ship, life support, reserve fuel, and science gear. At that point, a parachute isn't just difficult, it's physically impossible. No material can withstand the tension required for a chute hundreds of meters across. And even if it existed, Mars's atmospheric density couldn't generate enough drag. You're forced to use engines, and a lot of them. Then comes the worst nightmare, ascent from Mars. To lift a ship off the Martian surface and into orbit, you need about 4.5 to 5 kilometers ASE. That number is only slightly less than Earth's 9.3 kilometers but far more than ascent from the moon. And to fire from Mars orbit back toward Earth, you need another 1 kilometers/TARS. Total Delta V budget, 18 to 22 kilometers, sus 2 to 6 kilometers, sus Mars more than Apollo. But in the logarithmic trap of Tsiolkovsky's equation, that small difference becomes an abyss. Just a few extra kilometers can force you to triple, quadruple, or even quintuple the rocket's mass. And because fuel is heavy, you need more fuel to carry the fuel, creating an endless spiral engineers call mass cascade. NASA once described this clearly in their 2012 design reference mission. To deliver 1 ton of payload sitting still on a Martian surface, you need to place 20 to 30 tons into LEO. And to have 1 kilogram of fuel to leave Mars, you might need to bring 15 to 20 kilograms from Earth right from the start. That's the cruelty of Delta V. It amplifies every mistake, every kilogram, every wrong intuition. When I say we don't fail because of lacking technology, we fail because we underestimate the nature of the logarithm. I'm not joking, I'm just reminding you that the universe doesn't operate on our reasonableness. It operates on mathematics. And mathematics, as you can see, doesn't negotiate. And this is where things start to get truly harsh. Mars itself doesn't need to do anything to fight you. It just has to exist exactly as it is. Its distance is already a warning. In 2003, Mars was at its closest to Earth in 60,000 years, 55 million kilometers. But at other times it can be 401 million kilometers, away, nearly 8 times the most favorable distance. No crew, no current technology can turn back from that distance. And worse, you can't go to or leave Mars whenever you want. Earth and Mars only align for a launch window every 26 months, meaning if you arrive and realize you forgot something, an instrument, a tool, a ship part, you can't go back. You have to wait. And waiting on Mars isn't simple. To get there, the journey lasts 180 to 270 days in a ship with limited space, supplies, and repair capability. It's nothing like Apollo 11's 3-day trip to the moon. Every month you travel farther from Earth is a month you leave behind everywhere life has ever existed. But even if you survive that long journey, you still face the strangest atmosphere in the solar system. 0.6% Earth's density, thin enough to prevent effective braking, thick enough to burn up anything hitting it at 5.5 to 7.5 kilometers/s. That's why NASA calls the landing phase 7 minutes of terror. Because you can't intervene, can't adjust, can't call Earth for advice. Parachutes worked for Curiosity in 2012, but that was a 0.9-ton rover. A human mission will need 20 to 40 tons of supplies, equipment, habitat, and no matter how much NASA or SpaceX wants it, no parachute can deploy in Mars's atmosphere and generate enough drag for that mass. That forces us to rely on retropropulsion reverse thrust engines for 90% of the descent. But the fuel for braking is fuel you had to bring from Earth. And as you know, each kilogram of that fuel may require 15 to 20 kilograms of initial mass at launch. All just so you can touch down on Mars without becoming a new fine dust cloud in its thin red atmosphere. But even if you land safely, the planet keeps challenging you with something invisible but persistent: radiation. Unlike Earth, Mars has no magnetosphere, no natural shield protecting life from cosmic radiation. Over a 3-year mission, 9 months out, 500 days waiting for the next window. 9 months back, the crew would face 2 to 3 times the lifetime radiation limit NASA sets for astronauts. Galactic cosmic rays aren't light. They're heavy ionizing particles that can pierce metal, pierce bodies, and slice DNA like an invisible pair of scissors. We can't shield them with thin aluminum sheets. To reduce 90% of GCR, you need 2-3 meters of material mass that even Starship can't carry. Right now, even with major advances in launch technology, radiation remains an unbeatable enemy. And just when you think you've grasped all the physical hazards, Mars reminds you that humans aren't just machines of flesh. We are psychological beings, with communication delays of 4 to 22 minutes each way. Every conversation with Earth becomes fragmented, slow, emotionally out of sync. You can't ask, "What should I do?" and expect a timely answer. You have to learn to make decisions in absolute silence. NASA classifies this prolonged isolation as behavioral health risk class 1, the highest risk level, because it can't be eliminated by engineering or equipment. 4 to 6 humans in a confined space for 500 to 900 days, responsible for their own survival, knowing no one can come to rescue them. That's not just psychological burden, it's an existential stress no generation has ever faced. And if all that still isn't enough, there's one final, subtle but undeniable challenge of cosmology, not engineering: the loneliness of distance. Mars has almost no blue sky, no ocean, no sound of life. It's a world so silent you can hear the hiss of your air filter in the cabin. And for most of the journey, when you look out the spacecraft window, Earth is just a fragile blue dot, floating in endless darkness. I've always believed that sight isn't just scientific data. It's a ceaselessness of Paker's one hardware world that every step away from this planet is a challenge not just to our technical ability, but to human hope and imagination itself. We don't just face distance, we face the truth that the universe wasn't designed for life like ours. And Mars, for all its promise, remains a world where every element from atmosphere radiation to its very silence conspires to ask us one single question. Are you sure you know what you're doing? But all of that distance, atmosphere, radiation, isolation still isn't the biggest barrier. There's one problem most people don't think about, but it decides the entire survival of the mission: how to leave Mars and return to Earth. In space science, we call it the Mars return problem, and there's one truth I want to state clearly right up front. Getting to Mars is hard, but leaving Mars is much, much harder. You might imagine stepping onto the Martian surface as the moment of triumph. But in reality, that's only the first half of a fight, where the referee, the laws of physics, isn't on your side at all. To leave Mars, humans will need a Mars Ascent Vehicle, MAV, small but powerful rocket, to lift the crew from the surface to Mars orbit, where they can rendezvous with the mothership and begin the journey home. And that's exactly where Tsiolkovsky's equation, the tyrant I mentioned, becomes most merciless. The MAV needs to produce 4.5 to 5.0 kN/s of delta V. That's less than the 9.3 kilometers/ as a rocket needs to leave Earth. But don't let that fool you. The conditions on Mars are far from favorable. With the methane oxygen engines planned for future missions, the specific impulse is around 360 seconds, a good value but no miracle. With that figure, the MAV would need about 80% of its initial mass just for fuel. That means if the MAV weighs 40 tons, 32 tons of that is fuel. And if you think 32 tons of fuel is a big number, wait until you calculate backward to Earth. This is where things become literally absurd. If you try to bring all the ascent fuel from Earth, an idea that seems simple but is utterly naive, you run into the mass cascade chain reaction. With the required delta V, every 1 kilogram of fuel used to leave Mars may demand 15 to 25 kilograms of initial mass and LEO. This happens because you need fuel to carry fuel, and fuel to carry that fuel, repeating many times. So to have 30 tons of MAV fuel sitting on the Martian surface, you'd need to deliver 450 to 700 tons of initial mass into LEO from Earth. No human launch system, not even the most powerful ever built like Saturn V, SOS, or Starship, can put that much mass into orbit just for the return leg of the mission. And we haven't even talked about getting it to Mars, landing it safely, storing it, and using it. Bringing fuel from Earth isn't just technically impossible, it's mathematically impossible. But suppose you decide not to bring the fuel, and instead produce it on Mars itself, a smart strategy that NASA and SpaceX are pursuing. Then you face an entirely different problem: infrastructure. The MAV would have to store cryogenic fuel for about 500 days, while the crew waits for the next launch window. That's more than a year and a half in an environment with temperatures swinging from 20 degrees Celsius to 125 degrees Celsius, with ultrafine dust storms lasting weeks or months. On Earth, keeping tens of tons of liquid methane and oxygen cold is already a challenge. On Mars, there's no engineer coming every morning to check pipes, no technician to replace valves or fix leaks. Everything has to work perfectly without humans and endure the hostile environment for over 500 days. That's a requirement so high that no human-made plant or vehicle has ever achieved it. And even if the MAV and its fuel survive that long period, there's still the simplest but most critical question: how do you launch it? Mars is a dead planet, a frozen desert with no launch pad, no engineering team, no crane, no pre-launch checkout system. You have to launch a rocket from a distant planet where everything related to safety, ground support, and repairs is zero. That's why I once said, the problem isn't launching a rocket on Mars. The problem is launching a rocket that you've carried 55 million kilometers through vacuum. And then, after all those efforts, after storing fuel, protecting the MAV, surviving radiation, psychology, isolation, and successfully launching from Mars, you still aren't home. You've always felt there's a change, but at the atomic level, it's a ceaseless staple. Infantile challenge many overlook, Earth re-entry. When returning, your ship will slam into Earth's atmosphere at about 12 kilometers slash faster than any crew has ever experienced. Apollo 10 and 11 re-entered at around 11 kilometers slashes, and that was already the greatest challenge for 20th century human heat shield technology. But 12 kilometers station just a bit faster, it's 20 or 30% more kinetic energy, and energy never increases linearly. 12 kilometers tops is a speed where the plasma around the ship becomes so hot that no crude heat shield has ever been tested under those conditions. Even the most advanced TPS technology as of 2024 hasn't proven safe at the energy levels of a Mars return re-entry. And at that speed, you get only one chance. If the heat shield cracks, peels, or overheats, there's no repair time, no plan B. The ship will be destroyed right in the atmosphere you call home. When you consider all of this enormous delta V requirements, fuel that can't be carried, unrealistic infrastructure on Mars, radiation, atmospheric re-entry, you start to see that the real problem of a Mars mission isn't what the public usually imagines. Setting foot there, that's hard but within reach. The harder part, the one that truly reveals the cruelty of the universe, is leaving it. The universe doesn't need to build barriers to stop you. It's a staple, it's a ceaseless, be absolutely honest, and that honesty is written in Newton's laws, Tsiolkovsky's equation, Mars's red dust, and the vast distance no creature on Earth was ever designed to cross. So, when I say the problem with Mars isn't getting there, the problem is leaving it, I'm not just talking about engineering, I'm talking about a profound truth of the universe. Leaving an alien world has never been easy. Especially when that world doesn't want to keep you but also does nothing to help you leave. Right at the point where all the fuel numbers make you nearly despair, one idea emerges, like a faint beam of light piercing the darkness. ISRU, or in situ resource utilization. Harvesting resources right on Mars to produce fuel for the return journey. This is the most beautiful idea planetary science has ever produced. Instead of hauling tens of tons of methane and oxygen from Earth, make them on the red planet itself. Mars has an atmosphere that's 95% seal quartz, and if you have subsurface water, you can produce hydrogen. Combine K-borane and H-bor-K using the Sabatier reaction, a simple equation you can write in just a few characters. Say OH plus 4H-por AH plus 2H plus 2H-por-H, NH plus 2H-por-H, and oxygen for the engines. In theory, it's almost poetic perfection. You arrive on a new world and manufacture your own way home. But theory is safe. The real world never is. In 2021, during the Perseverance mission, NASA deployed a small device called MOX, a gold-colored box the size of a rice cooker, designed to extract oxygen from Martian atmospheric CL Parcoense. And it worked. MOXIE produced 6 to 10 grams of oxygen per hour. That was an engineering triumph, the first time humans produced a life-supporting and propulsion gas on another planet. But now contrast that with real needs. A Mars ascent vehicle requires roughly 30 to 40 tons of fuel for the departure burn from Mars, not 10 grams per hour, not 10 kilograms per day. You need to produce tens of tons of methane and oxygen on a world whose atmosphere is 170 times thinner than Earth's, whose climate is harsher than any desert we know, and where nighttime temperatures can plummet to 125 degrees Celsius. For ISRU to truly work at human mission scale, you would need an automated chemical plant the size of a shipping container, launched from Earth, landed safely on Mars, precisely deployed, and operated continuously for 500 days with 0 small failures and 0 human intervention. During that time, the plant must endure dust storms lasting 30 to 90 days, storms dense enough to block the sun and clog every surface, every joint, every filter. It must withstand day-night temperature swings of up to 70 degrees Celsius, repeated material expansion and contraction that can crack any weld. It's a ceaseless to cease, not leak, not get buried in dust, not freeze, and it must keep running, day after day, as though it was never designed to stop. On Earth, a chemical plant has hundreds of engineers, redundant systems, repair crews, and even then, things fail. A faulty sensor, a ruptured line, a stuck valve, that's normal. But on Mars, that normal becomes catastrophe. That's why I say on Earth, a plant failure is a problem. On Mars, it's a slow death sentence. Because if your ISRU plant breaks on day 120, or 270, or 499, no one is coming to fix it. No spare parts. No technicians. No hotline to NASA. And when a crew arrives on Mars after a 9-month journey, they will step onto the cold red ground only to discover that the fuel tanks meant to get them off the planet are empty. There is no way home. None of this denies the value of ISRU-1. The contrary, it proves how critical it is. Without ISRU, a crewed Mars mission is almost certainly doomed to fail. With ISRU, the mission is no longer outright impossible, but it remains extraordinarily fragile, like walking a tightrope stretched between two skyscrapers. The right path lies here. Build machines that can operate longer than any machine before them, in harsher environments than any before them, with higher reliability than any standard we've ever set. That is not merely an engineering problem, it is a philosophical problem of responsibility. If a tiny mistake can kill the entire crew, do you accept letting the machine run itself? And if not, you must send people ahead to check it, but they need fuel to return, and the logic loop returns to the starting point. This is the chasm between theory and reality. An idea can be beautiful to the point of perfection, but the universe does not care about that beauty. It only cares whether the idea can withstand to 125 degrees Celsius temperatures, Martian fine dust, time, and absolute isolation. And that question, as of now, still has no answer. When you pull all of this together, the non-negotiable distances, the atmosphere too thin to be useful, radiation that pierces metal, 22-minute communication silences each way, the fragility of human psychology over 900 days of isolation, ISRU plants that must operate flawlessly in an environment where even steel cracks under thermal cycles. When you string together the full delta V required to leave Earth, reach Mars, land, ascend again, and return, you begin to see the real picture. Mars has never been an adversary or an obstacle placed to block us. It is simply an unavoidable physical reality existing exactly as it has for billions of years before humans appeared. We are creatures who live by intuition, and our intuition was forged in valleys, beaches, and forests on Earth, not in the cold vacuum between planets. When we believe Mars is just a moon that's a little farther, we are not only wrong technically, we are trying to bend the universe to fit the scale our evolved guts find reasonable. But the universe does not do that for us. The universe is not complicated. It is merely honest. It does not want you to die. It also does not want you to live. It is only brutally honest. You can plunge into Mars's atmosphere at 7 kilometers Celsius, and that atmosphere lacking Earth's generosity will not stop you. You can live in a pressurized module for 500 days and galactic cosmic rays will pass through aluminum layers as though you weren't there. You can carry humanity's grandest hopes, but they will not convince Tsiolkovsky's equation to reduce the fuel mass you need. The universe does not negotiate, and it is precisely that stark honesty that makes Mars the ultimate test of our intelligence. Because for the first time in history, we face a goal that cannot be conquered by muscle power, by courage, or by recklessness. The very things that carried our ancestors across oceans, up mountains, and into deadly places, Mars is not Everest, it is a world where every decision is tied to equations that leave no room for emotion. You cannot outrun radiation by trying harder. You cannot overcome fuel shortages by taking a chance. You cannot bend hundreds of millions of kilometers of distance with optimism. If you are wrong, you die. No exceptions. And yet, right there in that ruthless honesty, there is something beautiful. Because if humans can return from Mars, if we can truly defy the gravity of two planets, overcome the delta V demands, survive radiation, push past psychological limits, endure the solitude of space, and come back to the blue oceans we call home, then that is not merely an engineering victory. It will be a victory of thought, a victory of the ability to look at the laws of the universe and accept that they are not enemies, but a language we must learn to live within this cosmos. And like every language, it demands we relearn what seems obvious, that distance is not kilometers, but months of isolation. That gravity does not just pull things down, but drags hundreds of tons of fuel along with it. That a seemingly simple chemical reaction demands an entire plant that must operate like a living organism. That the silence between two planets can stretch so long you hear your own heartbeat more clearly than any signal from Earth. It is within those limits that humanity will find its best version. Not because Mars gives us a destination, but because it gives us a mirror one that magnifies our fragility, our courage, and the stubbornness of a tiny species daring to challenge the coldest numbers in the universe. And if one day humans truly return from Mars alive, safe, carrying stories from that red world, then that moment will carry profound meaning. For the first time in history, we will have bent the limits the universe set at the beginning, not by breaking the rules, not by cheating the rules, but by understanding them so deeply that we use them to cross another world and come back. That will be the sign not only of a successful mission, but of a mature civilization, a civilization no longer bound by its evolutionary instincts, but able to reach outward, look at the universe with new eyes and say, "We understand you, and we will still go." If you want to keep exploring the universe through these honest and awe-filled perspectives, please hit subscribe so you don't miss the next part. Thank you for joining me. See you on the next journey among the stars.